Okay, so this is still recap, right? That incremental work done was force times dx, which can be written as PAdx or PdV. Okay? But for an entire process 1 say 2, the total work done is just going to be a sum of those incremental work dones, which is the integral of PdV for a process 1 से 2. ठीक है? So उसके बाद next step really is to calculate what would be the area under curves for different applications. So उसमें the first case that we are going to discuss, and actually we did this already, is going to be something called uh, isobaric process, which would be basically pressure is constant. So if pressure is constant, this integral is a really easy integral to compute, right? So W12 is going to be equal to the integral of PdV between 1 to 2. Pressure you can just take out of the integral and you're just left with PV, जिस पे हमने limits of integration apply करनी है, which means that the work done is just P into V2 minus V1. Very easy to see from the graph as well. A graph of pressure versus volume is just going to be a straight line between process 1 say 2, and the area under the curve is just going to be this part, which is very easily you can say that, like, you can tell that it's at pressure multiplied by the difference in volume between V2 and V1. Okay, so this was almost kind of nominal. The second example was something called an isothermal process, which meant that temperature is constant. So that means when T is constant, so by the ideal gas law, PV is equal to mRT. So if T is constant and these are also just constants, that means that isothermal process में the product of P times V is basically a constant, and that constant can be equal to P1 V1 or P2 V2 or any other point पे pressure times volume. ठीक है? इस constant की value on a PV diagram, a diagram which would actually look similar to the one showed up there, ठीक है? This constant is going to be equal to the product and pressure of pressure and volume at any point along this line. So इसमें the work done is once again the integral of PdV, right? Where you can write the, or you can replace P by that constant divided by V, right? From this equation up here, you can replace P by constant over V. ठीक है? हमेशा ऐसे ही करते हैं. If you got an integral over like some area or volume or distance or whatever physical quantity or whatever variable, तो आपके साथ जो जो दूसरी terms होंगी ना, you have to write every terms in terms of that variable. ठीक है? So that variable is V. So that means that the work done is constant बाहर आ सकता है 1 over V dV from 1 to 2, and that constant can be written, for example, as PV P1 V1, right? इसकी जगह P2 V2 भी लिखा जा सकता था, कोई मसला नहीं, but this constant I'm just going to write it as P1 V1 for now. ठीक है, और last time we talked about this, that 1 over x dx का इंटीग्रल क्या होता था? 1 over x का इंटीग्रल क्या होता था?
log x.
Yeah, natural log of x. ठीक है. So the integral of 1 over v is going to be natural log of v, and then you have to imply the limits of integration from 1 to 2, which means that the work done is going to be equal to P1 V1 times natural log of V2 minus natural log of V1. And the log x minus log y is actually log x over y, you might remember. So this means that this is equal to natural log of V2 over V1. ठीक है? I might want to add here that you can also rewrite this as P2 V2 natural log of V2 over V1, or you could use the ideal gas law, ठीक है, कि P1 V1 is equal to MRT अगर ये ideal gas की बात हो रही है, ठीक है, so you can rewrite this as MRT natural log of V1 over V2. Notice that if you write MRT, mass is the same throughout, R is the same throughout, and there's no difference between T1 and T2, ठीक है, so T1 is equal to T2. So बेशक आप P1 V1 is equal to MRT1 लिख रहे हो या P2 V2 is equal to MRT2 लिख रहे हो, they're the same, so you don't really need a subscript with your temperature because temperature is constant. ठीक है? So for an isothermal process, this is going to be the work done. ठीक है? अच्छा, I might also want to add perhaps कि अगर हम इसी की जगह small w लिख रहे हो, so small w means work done per unit mass. ठीक है? So all you need to do is replace, in this case, this volume by specific volume, or in this case, just mass cut jayega. So you're just going to be left with RT natural log of P2 over P1. Okay. If you use instead of capital volume, specific volumes within this natural log, it doesn't really matter, right? Because this is just a ratio. So within this natural log, you can rewrite this as small v2 over small v1, or if you got densities, you can just write it as rho 1 over rho 2. Order बदल जाएगा. ठीक है? Is all of that fine?
Yes, sir.
Okay.
सुमित
So
सर
जी जी.
सर ये तो ग्राफ्स बनाए हैं आपने ऊपर, ये पहला आइसोबैरिक का, दूसरा आइसोथर्मल का है सर, इसमें वॉल्यूम प्रेशर पे डिपेंडेंट नहीं होता दूसरे में?
Dependent. हाँ तो ठीक है ना, दोनों में there's a relationship between pressure and volume that we are showing, right? So यहाँ पे that relationship is दूसरे वाले में like volume, pressure और temperature पे dependent होता है ना. Temperature constant है, तो what we are left with is के P is equal to some constant over V, right? So hence this equation kind of looks like y is equal to 1 over x type की ना वाला curve. It looks kind of like that. टेढ़ा हुआ. So but it's also dependent on temperature. So volume is not just dependent on pressure; it's also dependent on temperature. Ideal
सर
gas
जो
law.
वो ओके सर.
जी.
सर ये वी फंक्शन है पी का या पी फंक्शन है वी का? वी फंक्शन है ना पी का?
देखिए, आप इसको इस तरह सिंप्लीफाइड तरीके से नहीं देख सकते एक फंक्शन दूसरे पे, लाइक दे आर इंटरडिपेंडेंट. ठीक है, प्रेशर वॉल्यूम एंड टेम्परेचर आर इंटरडिपेंडेंट बेस्ड ऑन the ideal gas law. So you can think of it as pressure is a function of volume and temperature. अगर mass constant है, पहली बात ये कि if we are talking about a closed system, or you can say that volume is a function of pressure and temperature, or that temperature is a pressure of volume and क्या रह गया pressure, right? So interdependent है तीन variables,
ओके सर.
right? चलो let me just keep that, it's okay. No need to erase it. So अभी हमने जो दो cases देखे हैं ना, these are both special cases of something called an isotropic process, I suppose, which is K if something follows the equation PV raised to the power n is constant. So अगर इसमें if I put n is equal to 0 in this ऊपर वाली equation, what that means is K P is constant, right? If I plug in, this was case 1. If I plug in n is equal to 0 in an equation, general equation PV n is equal to PV raised to the power n is constant, I get P is constant. If I plug in n is equal to 1 in this ऊपर वाली equation, I get T is constant. कोई question था?
नो सर, बाय मिस्टेक.
Okay. अगर T constant हो तो that was isothermal. अगर इनमें से ना n 0 हो ना n 1 हो तो फिर क्या करना है? वो अब उसके लिए दोबारा हमें कोई इक्वेशन निकालनी पड़ेगी, ठीक है? तो साथ ये भी लिख दूं कि दैट मीन के वर्क वाज इक्वल टू फॉर आइसोबारिक प्रोसेस P into V1 minus V2, for isothermal process P1 V1 natural log of V2 over V1, और ये जब ना 0 हो ना 1 हो तब क्या करना है और वर्क क्या होगा ये हमें कैलकुलेट करना पड़ेगा, ठीक है? So let me just, before we do that, let me just say कि we're not just doing math. This की एक example, एक important example जो कि हम आज डिटेल में डिस्कस करने वाले हैं, is going to be something called an adiabatic process. कुछ कॉन्सेप्ट्स आज होंगे वो इनकम्प्लीट भी छोड़े जाएंगे और बाद में रिपीट किए जाएंगे, बट कुछ चीज़ें आज ही दोबारा कवर नहीं होंगी, मतलब दोबारा एग्जांपल्स में आएंगी और प्रॉब्लम्स में आएंगी. सो do pay attention, this is important. So adiabatic process is one where there is no heat transfer. ये इतना लंबा लिखने की जरूरत ही नहीं थी. नो हीट ट्रांसफर, ठीक है? सो आइसोबारिक में प्रेशर कांस्टेंट था, आइसोथर्मल में टेम्परेचर कांस्टेंट था, एडियाबैटिक में देयर इज नो हीट ट्रांसफर. एंड इफ यू लुक एट आवर डायग्राम राइट हियर, ठीक है, तो if you just got pressurized gas in a cylinder, right, and it just expands because it's pressurized, the pressure is not going to remain constant. I'm going to have to do something, create some sort of a control mechanism to somehow keep the pressure constant, probably add heat to the system. Okay? And so this is not a reasonable explanation for this simple process of a gas expanding freely in an isolated cylinder. Okay? And neither is this, because you would expect that as this thing expands, you're going to see a drop in temperature. ठीक है? Remember the Joule-Thomson effects? Expansion के साथ you should expect कि अगर और कुछ नहीं हो रहा तो there should be a drop in temperature. So keeping temperature constant is actually, that would require me adding heat to it. ठीक है? वैसे we're gonna study problems later, but अभी से मैं अगर कहूँ तो you're gonna have to add the same amount of heat जितना fluid ने work किया है to keep the temperature constant. ठीक है? ताकि वो एनर्जी बैलेंस आउट हो जाए और टेम्परेचर ना गिरे. So if you're not even doing that, and if you got like an isolated cylinder, right, insulation हुई हो, uh, and you're experiencing expansion of a pressurized gas, so there is actually no heat transfer, right? At least ideally you could say that there would be no heat transfer, okay? And there would be no losses in the ideal case. So for such a process, it still follows PV raised to the power n is constant, where n is neither 0 nor 1. ठीक है? That is an example of an adiabatic process. और ये बात अभी भी जरा सी हवा में, obviously we are going to justify that much later on कि अच्छा क्यों अगर adiabatic है तो why would that follow pv raised to the power n is constant. We are going to justify that much later in like chapter 6 जब हम entropy पे बात करेंगे. For now we just have to accept this and move on to some extent and just पहले तो figure out कि what is going to be in that case the work done. So for a particular case of an adiabatic process, इस n की एक particular value भी होती है जिसमें हम 2 मिनट बाद आएंगे. Um, but for now, let's say कि for any n which is not 0 or 1, if p1 v1 is equal to p2 v2 raised to the power n, right? And which is basically a constant, and I have to evaluate the work done, which is the integral of p dv from 1 to 2, then I should replace pressure by some constant जिसको मैं इक्वेशन से इंटीग्रल से बाहर लेके आ सकता हूँ multiplied by the integral of 1 over v raised to the power n. ठीक है? I hope that makes sense. Pressure is a constant divided by v raised to the power n. So the question is, can we take an integral of v raised to the power minus n dv? और अगर आपको imagine करने में confusion हो रही है, just imagine it as x. Remember, right? v हो x हो क्या फर्क पड़ता है? Can anyone tell me what this is? Calculus का कोर्स अभी अभी क्लियर किया है आप लोगों ने?
Sir, v की power 1 minus n divided by 1 minus n.
v की पावर 1 minus n divided by 1 minus n, and you have to apply the limits of integration from 1 to 2. ठीक है? Okay, so those limits of integration, if I apply them, that becomes v2 raised to the power 1 minus n minus v1 raised to the power 1 minus n divided by 1 minus n. ठीक है? So now we are going to use a nice little trick, which is that this constant जिसको मैंने v2 raised to the power 1 minus n से भी multiply करना है और v1 raised to the power 1 minus n से भी multiply करना है, this constant is equal to p1 v1 raised to the power n or p2 v2 raised to the power n or any other value along the line जिस पे process हो रहा है. तो it's our convenience कि आपने कौन सी वाली value यहाँ पे select करनी है. So it's most convenient if you look at it, when you're multiplying it to v2, you just use p2 v2 raised to the power n. When you're multiplying it to v1, just use p1 v1 raised to the power n, right? Because that's going to make our equation look so much simpler. So जो पहली term है वो ये बन जाएगी. The second term is going to become p1 v1 raised to the power n multiplied by v1 raised to the power 1 minus n, and of course you're still dividing everything by 1 minus n. ठीक है? So what is the product of v raised to the power n multiplied by v raised to the power 1 minus n?
V raised to power 1.
Right? So n minus n कट जाएगा आपस में. And which makes this, reduces this to a much nicer looking equation, p2 v2 minus p1 v1 divided by 1 minus n. ठीक है? And you can think ये सारी जो बातें हमने 2 मिनट पहले की है ना, these also apply here, which means you can replace this by mr times t2 minus t1 divided by 1 minus n. You can replace p1 v1 by mr t1 and p2 v2 by mr t2, And then you could also say that if we are talking about the work done per unit mass, so a small w, right? Then you would just replace capital V by small v, or in this case, just mass delete हो जाएगा, right? So R into T2 minus T1 over 1 minus N. ठीक है? Okay. Yeah, if this makes sense, we can move on.
Yes, sir. You can move on.
Okay. So हमने बात की थी कि adiabatic process एक special case है जिसमें there is no heat transfer which also follows this PV raised to the power n type की equation. But for that adiabatic process, the value of n is gonna be the ratio of specific heats जिसको k का लफ्ज इस्तेमाल किया जाएगा जिसके लिए which is Cp over Cv. Now these terms might be new, so इस वजह से we need to talk about them. What are specific heats? ठीक है? And उस पे I'm gonna ask you to remember what was the definition of calorie. Remember calories? You know, it's stated on every meal that we, or not every meal, but like a lot of food items that we consume. So calorie की definition क्या होती है? किसी को भी याद हो?
Sir, 1 calorie is equal to 4.18 joules.
Kilojoules. अच्छा ये थोड़ा सा यार स्टूपिड डेफिनेशन है. कैपिटल सी से कैलोरी होता है, एक स्मॉल सी से कैलोरी होता है. सो ये कैपिटल सी वाला है ना वो 4.18 किलो जूल्स होता है. बट यस व्हाट इज मतलब ये होता क्या है? 4.18 क्यों डिसाइड किया है? इसकी पानी से कोई रिलेशनशिप होती है पानी को हीट अप करने से? डज एनीवन रिमेंबर दैट?
Amount of energy required to raise temperature of 1 kilogram through 1 degree Celsius.
ठीक. So this is like heat required to raise temperature of 1 kilogram by 1 degree. But the question is, okay, then what would be the heat required to raise temperature of, let's say, m kilograms by, instead of 1 degree, by delta T degrees? So अगर ये 4.18 है, तो for a process 1 say 2, what would be the heat required to raise the temperature by of m kilograms by delta T degrees? So 1 किलोग्राम के लिए अगर 4.18 किलो जाउल्स है, तो m किलोग्राम्स के लिए m मल्टीप्लाई कर दें. ठीक है? 10 किलोग्राम्स के लिए 41 किलो जाउल्स हो जाएगा, राइट? और अगर 10 डिग्री बढ़ाना है तो उसको भी मल्टीप्लाई कर दें, डेल्टा टी को भी मल्टीप्लाई कर दें. 10 डिग्री को अगर 10 किलोग्राम, सॉरी 10 किलोग्राम को अगर 10 डिग्री बढ़ाना है तो यू कैन एंड अप विद 418 किलो जाउल्स की रिक्वायरमेंट, राइट? ठीक है? सो व्हाट दैट मींस इज के द स्पेसिफिक हीट, राइट, जो कि यही है कि मतलब इसी कैलोरी की डेफिनेशन को आप फॉलो करें तो उसी तरह ही चल रही है. स्पेसिफिक हीट की जो डेफिनेशन है वो ये है यहाँ पे कि पर द किलो जाउल्स, जो कि 1 किलोग्राम को 1 केल्विन, केल्विन और सेंटीग्रेड बराबर ही है. इफ यू टॉक अबाउट द डिफरेंस बिटवीन लाइक 2 सेंटीग्रेड एंड द डिफरेंस बिटवीन, मतलब डेल्टा टी इज एक्चुअली इक्वल टू डेल्टा के. मैंने पूरे इक्वेशन के सामने लिख दिया. That was so inaccurate, right? I hope that's obvious. Okay, change in temperature is actually equal to sorry, changing temperature in Kelvin or Celsius is pretty much the same. अगर आप दो values के बीच में बात कर रहे हो, because the conversion is just you're adding something to it, right? So अगर आप for example कोई temperature difference calculate कर रहे हो, तो you can use either, you can use Celsius or you can use Kelvin, you're gonna get the same result, right? So SI units जो specific heats के हैं, that is kilojoules per kg Kelvin, जो कि liquid water के लिए, that means this, that the specific heat of liquid water is 4.18 kilogram, sorry, kilojoules per kg Kelvin. ठीक है? और that means that the uh, requirement, right, heat required, which is Q heat के लिए इस्तेमाल होता था heat transfer के लिए, for a process 1 से 2 is going to be equal to mc delta T, right, where C is your specific heat. ठीक है? यहाँ तक कोई इशू है? This is important, यहाँ तक कोई इशू नहीं होना चाहिए आगे जाने के लिए. So the problem is कि we are talking about liquids here. So liquid के case पे 4.18 is the single value of specific heat जो कि हमें चाहिए, and it doesn't even change all that much, really. But if we talk about gases such as ideal gases, then it's different if you make that calculation या observation basically at, let's say आपके पास एक टैंक है, मतलब वही पिस्टन सिलेंडर असेंबली टाइप की चीज है जिसके अंदर एक गैस है, ठीक है, एंड आप दो तरीके से इसकी मेजरमेंट करते हो. वन इज दैट यू कीप द प्रेशर कांस्टेंट, ठीक है, एंड यू हीट इट अप, और इट्स अलाउड टू एक्सपैंड, ठीक है, बिकॉज प्रेशर कांस्टेंट है, व्हेन यू हीट समथिंग अप इट्स गोना एक्सपैंड, ठीक है. तो इन दैट केस इफ प्रेशर इज कांस्टेंट, then the value of specific heat is going to be called Cp, which is specific heat, hat नहीं है, heat है, at constant pressure, ठीक है. और अगर हम वॉल्यूम को कांस्टेंट कर दें, then the pressure is not constant. We have fixed the volume. When you heat up the gas, it wants to expand, but it can't really expand, right? So it's going to get pressurized instead. But in that case, volume is constant, pressure is no longer constant. Then the specific heat is going to be called Cv, which is going to be the specific heat at constant volume. ठीक है? The reason they're pretty much the same for liquid water is that liquid water doesn't really expand all that much. ठीक है? उसमें expansion, density का change कोई खास ज़्यादा नहीं होता, volume का change कोई खास ज़्यादा नहीं होता, ignorable होता है roughly. ठीक है? So there's no real difference between the specific heat at constant pressure and volume, but in gases, expansion plays a major part, and expansion, is involved with work, right? So there's going to be a difference between these two, and Cp is normally greater than Cv. Okay? So the ratio of these two is going to be called the ratio of specific heats. The difference between these two is going to be actually the gas constant. Remember gas constant R? That's actually going to be the difference between specific heats at constant pressure and volume. ठीक है. सो ये बातें थोड़ी सी इनमें मजीद एक्सपेंशन होगी बहुत बाद में, मगर थोड़ी सी हम आज बात करेंगे. स्पेशली ये जो आर वाली बात है ना, तो आउट ऑफ नोवेयर ही कही गई है, तो इफ दैट सीम्स आउट ऑफ प्लेस तो खैर होती है, इट्स ओके, वी आर probably going to talk about it again later. Not sure if it's necessary, but still. But any questions अभी तक? Okay. So I suppose एक नया पेज क्रिएट कर लेते हैं. So अभी तक हमने ये स्पेसिफिक हीट पे बात कर ली. अब अगर मैं एक एनर्जी बैलेंस करूं कि लेट्स से वी आर डूइंग heat addition, case 1 type, heat addition at a constant volume. ठीक है. अब उसके ऊपर you're doing an energy balance, so the energy balance says कि delta E is equal to Q12 minus W12. But if you're talking about a stationary system, this delta E becomes delta U. Right? If kinetic and potential energy effects are not that high, not that important, mostly internal energy का फर्क आ रहा हो. So this is what it becomes. And then if you are talking about a constant volume process, by the way, a process that is constant volume is going to be called isocoric process. एक और iso का लफ्ज बहुत सारे आएंगे, याद रखने सारे, which is के constant volume process. ठीक है. So for a constant volume process, what is the work done? कोई मुझे बता सकता है? No lengthy calculations needed.
Zero.
Zero, because there is no volume change, so this dv term is pretty much zero. It's if you look at a PV diagram, right? So all that's happening in this heat addition at constant pressure, sorry, at constant volume, is के PV diagram पे you're moving vertically upwards. ठीक है? So the area under this vertical line is, zero. ठीक है? So since there is no work done, that means that a change in internal energy is just going to be equal to ये heat added. ठीक है? And this heat added is going to be equal to mCV delta T for a constant volume heat addition, because that's where this whole definition of CV came from. कि अच्छा एक second, मैं volume constant रख के I want to see how easily things heat up, right? So the heat added in constant volume heat addition is just going to be equal to the specific heat multiplied by जितने mass को मैं heat कर रहा हूँ multiplied by जितना temperature मैंने increase करना है. ठीक है. अच्छा, अब the problem with this is that the value of CV actually depends on temperature, so you can't use really high values of delta T for this. So अगर मैं इसको more precisely लिखने का तरीका ये है कि, and by the way I should also be very careful about this, I'm never careful about this. यहाँ पे we are talking about capital U, और मेरे capital U और small u में जो है ना फर्क बड़ी मुश्किल से नजर आता है. So my capital U won't have this little tail. Small u में tail हो सकती है. If I make that mistake, so let me know. If you're reading the book, no problem, right? But if you're writing on with pen and paper, so this is important. ठीक है? So this leads to our actual definition of CV, which is कि ये अगर मैं mass को divide कर दूं और delta T को भी नीचे ले आऊं, तो this capital U is going to become small u, and then CV is going to be equal to du by dt evaluated at constant pressure. ठीक है? And this is always true. Both of these things are always true for like ideal gases in closed systems. कि एक तो ये कि delta U is equal to CV delta T, ये small है, ठीक है? या अगर ये capital हो जाए तो mCV delta T, and this दूसरा है कि CV is du by dt for constant pressure. ठीक है? Is this fine? Is this result okay? So ये हमारे दो end results आ गए इस line of thought के.
सर ये एंड से थोड़ा सा दोबारा एक्सप्लेन कर सर, ये एंड से ये
अच्छा
सेकंड वाला।
ठीक है, I'm gonna be very quick about it this time. So जो energy balance है that stated कि delta U is gonna be equal to Q12 minus W12 for a stationary system. अगर हम heat addition at constant volume कर रहे हैं तो work done 0 हो गया, so that means कि change in internal energy is just equal to the heat added. जो heat added है वो अगर volume constant है so that's going to be equal to just mass multiplied by CV, which is specific heat at constant volume, multiplied by delta T, just based on our idea कि अच्छा specific heat किस तरह calculate करते थे, किस तरह observe करते थे. प्रेशर कांस्टेंट करके हीट करो, देखो क्या होता है, तो फिर उससे स्पेसिफिक हीट एट कांस्टेंट प्रेशर कहते हैं. वॉल्यूम को कांस्टेंट रखो और देखो क्या होता है, तो उसे स्पेसिफिक हीट एट कांस्टेंट वॉल्यूम कहते हैं. ठीक है. So in our case, we are heating something at constant volume, then heat added is going to be equal to capital Q, right? Is going to be equal to mCV delta T. ठीक है. So
यस सर।
that leads to our two important definitions. एक तो ये कि ये capital U था, अगर मैं मास से divide कर दूं, then you can say that delta U is equal to CV delta T, and this is true for यही क्या कहते हैं closed system ideal gas के लिए. This is totally fine. And then ये तो ये जो value of CV है ना, this actually depends on temperature, so you can't really use this for really large temperature differences. तो इसको exact तरीके से लिखने का तरीका का ये है कि just replace these deltas by ये differential वाले symbols, right? So du is going to be equal to mCV dt. ठीक है, which means के CV is going to be equal to capital Du divided by mdt, which is du by dt for pressure is for constant pressure. ठीक है.
सर ये फॉर कांस्टेंट वॉल्यूम नहीं आएगा?
यस, हाँ सॉरी, बिल्कुल सही कह रहे हो, हम कांस्टेंट वॉल्यूम पे बात कर रहे हैं. हाउ डू आई मेक द सेम मिस्टेक ट्वाइस? थैंक यू. कांस्टेंट वॉल्यूम. अब हम बात करने वाले हैं कि व्हाट हैपेंस एट, थैंक यू फॉर पॉइंटिंग दैट आउट, व्हाट हैपेंस एट कांस्टेंट प्रेशर. सो उस केस में यही डेल्टा ई जो कि चलो फॉर स्टेशनरी सिस्टम डेल्टा यू is going to be equal to Q12 minus W12, but यहाँ पे for constant pressure process work done क्या होता है? पिछली स्लाइड पे हमने डाला था, just pressure times the difference in volume. ठीक है, so you can call it P into V2 minus V1, और थोड़ी सी हमारी कन्वीनियंस ज्यादा होगी कि हम इसे लिखे P2 V2 minus P1 V1. ठीक है, P2 और P1 बराबर है, so you can easily मतलब write it like this. ठीक है. So that means K, and if I take it on the other side, I'm going to get delta U plus W12 is equal to Q12. ठीक है. So now I'm going to make a couple of substitutions really quickly. एक तो ये for a process 1 से 2, जो heat addition का process हम constant pressure पे कर रहे हैं, delta U is going to be equal to U2 minus U1, and then this work done comes from this isobaric process. It's going to be equal to P2 V2 minus P1 V1, right? So ये delta U जो है ये बन गया, work done ये बन गया, and then the heat added for a constant pressure process can be written as m c delta t, but remember चूंकि हम constant pressure पे बात कर रहे हैं, so cp लफ्ज इस्तेमाल करेंगे. ठीक है, because sort of by definition of specific heat at constant pressure. ठीक है, okay, we're doing heat addition at a constant pressure, so the heat added is going to be equal to the specific heat multiplied by कितना mass था, multiplied by कितना temperature बढ़ाना था, and we are doing this at constant pressure, so that's going to be called specific heat at constant pressure. ठीक है? Is this okay अभी तक? Okay. And once again, I keep doing this. ये है तो capital, but just to clarify कि capital या get rid of these tails, right? So that means कि U plus PV का जो difference है ना, वो इस MCP delta T के बराबर है, ठीक है? And since this isn't actually the first time कि internal energy में P into V multiply हो रहा है, इस वजह से we just gonna define because it is convenient. So we just gonna convenience की वजह से define enthalpy, which is gonna be given a simple symbol H as H is equal to U plus PV. And that is really the definition of enthalpy. Enthalpy इसके अलावा कुछ खास नहीं है कि internal energy लो जिसका हमें फिजिकल मीनिंग पता था, उसमें ऐड कर दो उस स्टेट पे प्रेशर और वॉल्यूम का प्रोडक्ट, एंड दैट इज योर एंथैल्पी, ठीक है? सो अब उसको बाद में अगर किसी ने हीट ऑफ वेपराइजेशन करना है या एनर्जी ऑफ फ्लोइंग लिक्विड कहना है या कुछ कहना है, वो इस वजह से बिकॉज वो एप्लीकेशंस जहाँ पे वो चीज़ नज़र आ रही है ना, ये प्रोडक्ट नज़र आ रहा है, उसको देखते हुए लोग और बातें करते हैं कि what is actually enthalpy, but its actual definition is very simply it's just U plus PV, and it's done because it's convenient. Every now and then you have to make this calculation, so instead of calculating it every time, why not just पहले से जो है ना एक अलग नाम लेके अलग से एक टेबल क्यों ना बना दें हम इसका, सिर्फ मैथमेटिकल कन्वीनियंस है, ठीक है? So that's all what enthalpy is, U plus PV, and that means कि if I divide it by mass, so per unit mass में मैं इसे देखूं तो it's gonna be small u plus p into small v, ठीक है? So that means कि this is just h2 minus h1, ठीक है? Which leads to जिस तरह यहाँ पे du was equal to mcv delta t, यहाँ पे dh is equal to mcp delta t, या small dh is equal to cp delta t, और exactly उसी तरह cp की definition बन जाती है dh over dt calculated at, उल्टा बोल रहा हूँ दोबारा से, pressure is constant, ठीक है? All of this makes some sense? Any questions here?
Yes, sir.
I suppose this is a good enough time for a break, so I'm going to turn the recording off.